Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by satsearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organizations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello and welcome to the episode. Today I'm joined by Edwin Faier of Xiphos Systems Corporation, a Canadian manufacturer of onboard computers and processors and a satsearch member. Today we're going to talk about advancing the use of FPGA-based OBCs in space applications. Now, FPGA stands for Field Programmable Gate Array and is basically a form of integrated circuit designed to be configured by the user in the field as needed. So firstly, Edwin, thank you for being with us today. And is there anything you'd like to add to that introduction?
Well, first off, I just want to thank you and satsearch for the opportunity to join you to talk about this. Xiphos has been providing powerful processing, FPGA-based processing solutions for over 20 years. We're kind of the grandfathers, I think, of new space. That's what I like to say. And we've been in over 40 different LEO missions across our product line. Basically, what we focus on is providing swap-optimized products that use industrial-grade, COTS components in a fault-tolerant architecture that can be deployed in harsh environments, space, obviously, but so providing very robust performance, but at a fraction of the cost of your typical space grade solutions.
Well, so perfect. So let's dive into the topic today. Now, traditionally, sort of standard microprocessor and microcontroller-based architectures have been used in space missions, and particularly in small satellites. What advantages do FPGA-based OBCs bring to space missions as an alternative?
The main advantages are with respect to scalability, performance, and most significantly, flexibility. So in general, any microprocessor-based solution is, or microcontroller-based architecture is flexible, right? Because it's based on software, and the software provides a vast amount of flexibility, and including the ability, for example, to upgrade your code in orbit if you had to. So that's an important feature. Obviously, processor-based or microcontroller-based systems are obviously a step above, kind of bespoke, application-specific hardware solutions. Even if it has FPGAs, because typically in those solutions, the FPGAs are what's called anti-fuse based or flash based, so they're programmed on the ground, generally not programmed in orbit. So obviously a software-based solution provides that additional flexibility. But designing around an FPGA-based OBC, it really provides the ultimate in flexibility, and for many reasons. So first of all, generally, it's an OBC. It has an embedded processor, so it has that same software capability. But at the same time, the processor and software is very tightly coupled with a massive amount of available FPGA resources. And like you mentioned, it allows you to reconfigure, it allows you to design logic that is specific to your application. So first, the real-time speed of the FPGA coupled plus the tight coupling to the processor just increases the overall performance, right? And flexibility, right? You have software and FPGA. So effectively, when you're coming up with your application, you can design your logic and the software to the specific needs of the mission. The other thing that's interesting about FPGAs in general is that even the I/O itself is flexible. So each pin can be reconfigured or configured to a different type of I/O depending on your needs for your speed, depending on what you're interfacing to, and so on. So, that also provides a huge amount of flexibility, right? So you've got the software, you've got this configurable FPGA logic, you've got the I/O pins themselves, which you can configure to different technologies. I'll talk about some of them later. And in fact, just like the software can be updated in orbit, in this particular case, we're talking about both the software and the logic having the capability to be updated in orbit. So again, adds to the flexibility, adds to risk reduction. If you go back 10 or 20 years, if you were designing with a anti-fuse-based FPGA, once it was programmed on the ground and it launched, that was it. You couldn't do anything about it. So there was a huge amount of risk. The amount of verification and validation obviously was maybe an order of magnitude higher than what it has to be when something is reconfigurable. That's the main thing. So again, scalability, performance, and most significantly flexibility.
Important, benefits and objectives that many different new space companies have for their technology. So it's interesting to see it in that area. Now, another sort of aspect of this, we're seeing lots of approaches for space missions based on system-on-a-chip technology or system-on-chip technology. I've seen both versions used. I wonder if you could just briefly talk about the architecture of FPGA-based system-on-chips and their applications in space.
Yeah, sure. That's a good question, and it's very much a modern question. So, like I said, Xiphos has been doing this for 20 years, right? And if you go back along its product line, you'll find processor-based solutions that effectively, in general, it always has an FPGA in the middle. But the difference was that in some of the previous solutions, including even just the previous generation, it was a pure FPGA. So now, you can take an FPGA and turn it into a processor solution. You can turn it into an OBC, but it requires the use of what's called soft IP cores. So these are logic IP cores that are integrated into the FPGA to perform the processing functions, maybe some of the peripheral functions, and so on. The problem is that you're using up a lot of valuable FPGA resources. So you're stealing FPGA resources for the processor function, but so what you have left is is much smaller. So if you have some application-specific logic you have to develop, well, you've just used up a lot of your available logic. And also, because you're using logic resources, generally, you don't have the speed. You cannot run a FPGA's processor at the speed of a, ASIC-based processor. So that's where system on a chip comes in. So with the reduction in, going now to 16 nanometer and smaller types of silicon processes, it allows a much higher level of integration. So effectively what a system on chip is, as compared to just a standard FPGA, is the fact that it's a hybrid solution that has what are called hard IP cores. And those hard IP cores form the complete processing system. So those are effectively an ASIC, right? That's embedded on this die, and around it is all the available FPGA resources. So on a single die, you have the FPGA resource, and now even more massive FPGA resources embedded on the same die with ASIC-based processing cores. Okay, so that effectively is the system. That's why it's called the system on a chip, because it includes all the components, and I'll get into that in a second, what's required for a processing system. What happens is, in that case, so now the processing function itself is actually an ASIC. So now it runs at full speed. It doesn't suffer the constraints of, using FPGA logic, which kind of slows it down. And because it's so tightly coupled, it's on the same die as the FPGA logic, the mutual performance is higher as well. So you get another benefit, another increase in performance, right? So the FPGA logic, which basically runs in real time in nanoseconds, and then you've got the processor, which is now an ASIC, so running in its true true native high-speed mode, and then the coupling between them, because they're on the same die, is very efficient and fast. So overall performance is increased. So if you look at a SoC FPGA, if you take a look at the hard cores that are in there, you'll find everything that you'll need on a standard, either that makes up a processor or that is required around the processor. Typically you'll see some elements in a microcontroller, right? So it's kind of a single chip processor with external memory and stuff. But so that's kind of the same basis. So the systems on a chip, the hard cores would include the processors themselves, level 1 and level 2 cache, so L1 and L2 cache. Typically, it has some onboard high-speed memory that's SRAM based, so it's a lot faster than going out to your like DDR memory. It's got external memory controllers, and those typically, especially from the more modern FPGAs, will support your DDR RAM, whether it be DDR2, 3, 4, and so on, in multiple configurations and sizes, along with the support, for example, of error correction coding logic, like ECC. Those are built into these hard cores. It'll also support NOR flash, external NOR flash for program memory, where you'll store your software and when you actually store your firmware for the FPGA. And also it'll support external NAND flash for, kind of non-volatile memory storage, mass memory, if you like. There's even, for example, controllers for like eMMC if you need mass memory. And then you'd also have the standard set of peripherals like timers, interrupt controllers, DMA controllers, and a broad range of peripherals and interfaces. So those are typically what would be included, like some of the terminology you'll see in some of these FPGAs in the processing section. Okay, the PS, whereas the programmable logic section has the logic, the PS has all of these hard cores. So because all of these subsystems, the processing subsystems, are implemented effectively in an ASIC, their performance is maximized. And so you take that maximum performance, you combine it with the programmability of an embedded FPGA. You have the ability to select the I/O type and so on. So you pretty much have ultimate flexibility for kind of really a broad range of space applications. And then on top of that, like I had mentioned before, the fact that you can reprogram both the logic and the software in orbit allows you, not only as a mechanism to correct mistakes or whatever, but I think more importantly, it provides you for an upgrade path for your mission. So you can launch it, and then you can upgrade with capabilities as as your business plan advances, as you get new customers with new requirements, you can actually adapt it and upgrade in the future. Yes, it was a long answer, but I hope it kind of differentiates, what a system on a chip FPGA is versus a standard FPGA, and then obviously compared to just a standalone processor.
Yeah, absolutely. I think that was a really thorough overview of the architecture there. So thank you for that. And obviously, a lot of what we talk about in space missions comes down to trade-offs, and you mentioned that this was probably a lot of the motivation for the development of FPGA-based OBC systems is how do you cope with these trade-offs? How do you produce innovation that can remove the limits to some extent that are put on you by other technologies? So aside from the lots of things you've mentioned in terms of flexibility and upgrade paths, etc., I wondered if you could describe any of the other advantages of designing, FPGA-based multiprocessor systems on chip.
Okay, so flexibility obviously is a key thing, but in effect also, if you look at the modern, the newer, more advanced systems on a chip. So for example, I think a good example, and I think a lot of people in the industry are aware of it, is the Xilinx Zynq UltraScale Plus. So this is a very powerful FPGA system on a chip. In fact, it's a multiprocessor system on a chip, which we'll talk about a little more soon. So we use that on a couple of our products. One is called the Q8, and the other one is called the Q8J. These are both processing solutions, little OBCs based on the UltraScale Plus. So these processors contain the multiple multi-core ARM processors. So it's got, for example, a quad-core application processor, a dual-core retime processor, a GPU. So 7 processors in one single device. So that's a lot of horsepower that's available to like really advanced applications, right, that need it, right? And on top of that, in terms of the systems on a chip, it includes traditional interfaces like, serial ports and I2C and SPI and general purpose IO, the type of stuff you'd see on microcontrollers. But it also provides kind of a suite of like really high performance peripherals and interfaces. So you've got like multiple gigabit Ethernet MACs. You've got a couple of CAN bus cores. You've got USB 2. You got USB 3 built in, and you've got high speed PCIe. So when you add all these interfaces, like if you did this in an FPGA, for example, like a standard FPGA, you would have, either you need a massive FPGA, or you would have absolutely nothing left to develop anything else in there. And on top of it, just the development effort to integrate it and test it and so on into an FPGA would be, it's a large engineering effort. Here, they're built into the device, right? So what that does is really allow a very broad range of applications. So you can imagine with CAN, which is quite typical, but when you start adding, gigabit Ethernet multiple ports, when you start adding USB 3 and so on, and a lot of other cores that I'm not even mentioning here, the application set is enormous, and it can meet, generally the performance requirements of many, many types of interfaces. So, and then you look at the I/O itself, right? Like I mentioned before, the different types of I/O. Do you need low voltage TTL? Do you need low voltage CMOS, LVDS, because you want to run it, you want to run it a gigabit per second? Or what if you have, multi-gigabit per second I/O that you want to interface to, for example, a very, very high-speed sensor? It's there. It's available. So you can really design your system to pretty much match up with any type of suite of sensors or actuators or and so on, right? Because of that, the flexibility and just it's a very powerful set of tools that you have to work with. And on top of that, you have the FPGA stuff, the massive FPGA logic that's available. So really, you end up with this core solution that can be configured really to meet pretty much the requirements of any application. And we'll get into that, I think, maybe a little more later, I'm sure.
Well, yeah, that was actually going to be my next question. So could you, discuss some of the examples of the use cases and applications that FPGA-based systems on chips, OBCs, have been used for, or either that you've seen or that, that you can talk about that are in development, if you're happy to?
If you imagine it, it can be done. That's. But in terms of what we've seen in real life, I can touch on that. But first, I just wanted to, because if you talk about some of the use cases, I think one of the things that's important is to differentiate a solution to, for example, a traditional processor-based OBC. So I think once we understand that distinction, and already touched on some of it, but some of the other things is more of an architectural level thing, and it's where FPGAs shine again. So if you look at a traditional OBC that's, let's say, processor-based only, right? So generally, you'll have a processor on a board, and if you want to be able to integrate a system relatively easily, that'll have some type of bus interface, right? The OBC, right? So it could be compact PCI. Like there's many, compact PCI has been around a long time. It started in the industrial market and was, adopted in the space market. More recently, VPX, and now even more recently, space VPX. So you have a processor, which is just the processing engine with a bus that board would then interface to a backplane. And then you would expand your system by sticking in peripheral cards that support that same bus, so you have that same bus interface, whether it be compact PCI or whatever. So typically there's kind of a complex, either logic could be done in FPGA or in a specific application-specific chip to interface with the bus, and then you can stick on a bunch of peripherals if you'd like. If you want analog to digital converters, if you need specific, like if you needed a CAN bus, you might find a peripheral card with a CAN bus and so on. So you expand it by populating your backplane with the peripheral cards that you need for your mission. So it in a certain sense that it's kind of a systems engineering job, putting all these things together. And very often, the traditional OBC people will have kind of these bespoke, available off the shelf peripheral cards. So yes, it's expandable, but as you can imagine, it does so at the expense of size, weight, power, and effect performance, right? Because you've got this processor decoupled by a bus, so you're then limited by the performance of that bus, right? And then how many things can you put on the bus? There's a lot of constraints around it. So that's a traditional OBC. You typically see these boxes, whether it be like a 3U or 6U box, where that would be just the processor with all of its different peripheral cards in a chassis, right? So that's your traditional system. Now, in comparison, if you look at a subsystem that's made out of an MPSoC, FPGA-based OBC, everything is much more tightly coupled, right? So everything is very highly integrated, and it's truly embedded, right? It's not, it's not, distributed across these multiple, peripheral cards. So all of those interfaces, whether it's a CAN bus or you need to interface to an ADC, or you need SpaceWire, you need camera link, those would generally be done on an interface board. In this particular case, those things are all done in the FPGA, and the interconnects between these interfaces are in the FPGA. So obviously, all that capability, which was spread across multiple boards, is now effectively, including the processor itself, embedded in that multiprocessor system on a chip, with its associated FPGA logic. So obviously, what does that do? It's a massive step in the reduction of swap, right? So size, weight, and power, effectively, like our Q7 processor is 23 grams, the size of a credit card, right? So, and then a board that would be associated with it could be about the same size, right? So it's very, very small, highly integrated. So you have much lower size, much slower weight, much lower power, and of course lower cost, right? You don't have all these peripheral boards, a backplane, and so on. So what does that give you? Well, if you look at the small sat market, whether it be universities or even companies, who are launching commercial ventures, are launching 1U satellites, or launching 3U or 6U. I mean, the traditional OBC, it's bigger than if you want to put a solar panel on the OBC and fly it, you can try, but it's not going to fly very long, right? So what this does is it enables that processing power, all that performance, to even work on a CubeSat, which is not possible with your more traditional OBCs. Now, I just wanted to give kind of an overview of what does a subsystem look like that would have an FPGA or MPSoC FPGA-based OBC in it. So if you take a look at our Q cards, like the Q7 or Q8, those are our processor products. They're credit card size, or maybe double credit card size processor boards that contain all of the core processing and FPGA capabilities, and those effectively embedded within that MPSoC, right? The board also contains obviously all the memory that you require to operate your processor, and it also along with power supplies, it also has a lot of supervisory circuitry and stuff that allows us to use these COTS boards in space, right? So with radiation and so on, right? So we have a lot of fault recovery and stuff like that. Now, most of the I/O that's available from the FPGA comes out of a mezzanine connector on the bottom of the Q card, right? So the processor board itself doesn't have a lot of I/O, right? It has a lot of I/O coming out of the bottom of it, but in terms of I/O you connect with, it's limited. It's really only like maybe Ethernet for RJ45 if you want to use it for development, but you wouldn't use that in flight. You would use that on the daughter board. So the Q card itself would connect to a custom daughter board, and that custom daughter board would provide, the required interfaces, connectors, if you need some extra functionality on that board, and the form factor that's required for your mission. Like if it's a 1U CubeSat, it would be a 1U size board, and then you would mount the Q card on top of that board. So the processing function is separate, and the daughter board itself is what has all the application specific stuff. And the size of that daughter board is really driven by, well, maybe there's a mechanical form factor you have to meet, or generally it's driven by how many connectors you need in the interfaces, right? So, so that's a typical what it would look like, okay? And so you compare that. So you can have a board that's, maybe 50 millimeters by 100 millimeters by 12 millimeters high in terms of a set, and that's your OBC, as opposed to maybe a 3U or 6U backplane based system, so much smaller, right? So it can fit on a CubeSat. So in terms of applications, because you asked me about applications, so general types of stuff, controlling cameras, interfacing to cameras is very common. So sensors, hyperspectral instruments, other types of sensors. Because you have the processor on board, plus FPGA, you can do onboard processing. And I'll talk about that as well later. Software-defined radios, that's a very common application right now. And that could be for like IoT, Internet of Things. That could be for broadband communication. That could be for RF sensing, whatever, whether it's a receive transmit or just a receive radio. So these boards are very well suited for that application. Satellite-based science, ISS-based science. We have multiple systems on the ISS right now as we speak. And then, of course, now today, which is all the rage, robotics, lunar applications such as landers and rovers, et cetera. So, in fact, pretty much like I had mentioned, the applications are endless. And one particular, I'm making this a long answer, but one particularly interesting use case, which is not really possible with a processor-only based solution, is something that it's effectively hardware-accelerated onboard processing. So, at Xiphos, we call that hybridization. So, effectively, what we're doing is we're leveraging the real-time processing capability of FPGA logic to accelerate very complex software algorithms. So, like usually on the ground, you develop an algorithm on a i7, an Intel i7 processor that's, burning 200 watts, right? The problem is, okay, so how do I take that algorithm and now run it on a 2 watt or 5 watt space compatible processor? I mean, you can't, right? So that's where hybridization comes in. So what we do is we actually take a look at the algorithm. We look at what the processor is doing. You can identify where it's spinning it, turning its wheels, spending its time. And you could look at those specific functions and say, okay, can I take that function out of software and actually accelerate it in hardware? Can I put things in parallel? Can I pipeline it? There are certain things that software does that is easily accelerated in hardware. Certain things are better suited in software, so you leave it there. And then what you do is you kind of trick the software into thinking it's running software, but in fact, it's a combination of software, but then for those critical, very time-consuming, real-time things, it's actually being run in the FPGA. So we've accelerated multiple algorithms doing that. So we could take something running on an i7 and run it on the Q7, which runs at 2 watts. And we've done things like hyperspectral compression algorithms, location orientation, like for in-orbit satellite servicing, or docking to the space station, for example. You got to be able to orient something that you're coming up to. Feature tracking, which would be used maybe for visual odometry or autonomy for a rover as it's roving around. Quantum key stuff. We've accelerated some privacy amplification things and a whole bunch of image processing. So that's something that is really unique and leverages the hybrid logic processing capability of a MPSoC FPGA. Very long answer to your question, but I think hopefully I've covered the gamut.
Yeah, no, absolutely. Well, illustrative of just this huge array of functions and use cases that these systems are suitable for. And it's kind of, that's on the one hand. On the other hand, as you mentioned, there's such a focus on the low swap value, credit card size systems, So marrying those two requirements and looking at it from a commercial sense, is it possible for these systems to be considered as or developed as COTS solutions for certain applications, certain mission profiles?
Well, in all honesty, I would say the future is now. It already is. It already has. Yeah. So if you the MPSoC FPGA-based OBCs, such as like the Q7 or Q8, I mean, they're COTS products, right? They're available off the shelf. It's a processing engine, right? What you do with that, processing and FPGA engine. So what you do with that is really dependent on your end application. So I'll give one example, which is becoming, when you talk about being standardized on these COTS solutions, one good example is software-defined radios. Okay, so using an MPSoC FPGA-based OBC, using that combination of processing and logic, it's becoming the kind of the de facto standard for implementing like new, modern, high-performance software-defined radio designs or SDR designs. So if you look at if you blow up an SDR, what is it? It's the FPGA, it's the processing, and then it has generally an RF wideband transceiver chip. An example, Analog Devices has a variety of these of different performance levels. So when you take those wideband transceiver chips and combine it with the FPGA and processing horsepower, it's the ideal SDR development environment. So you just got to add in your RF subsystem, your LNAs and your power amplifiers, and you've got a very powerful but flexible SDR, right? So your SDR could be used, like I mentioned before, Internet of Things, wideband RF sensing, broadband communications, really runs the gamut, right? 5G, I guess, is going to be the big buzzword these days too. 5G some space. So much so that I had mentioned the Q8J. So we developed the Q8J processor, which is a variant of the Q8, really just to kind of meet the requirements of kind of these advanced SDR platforms. Now, if you take that one step further, another kind of buzzword you hear about, and this has been enabled by this thing, and I'll call it revolutionary. I don't think it's not really just marketing; it really is revolutionary. Is a term called software-defined satellites. It's not just software-defined radios, but so what's a software-defined satellite? Well, it's a software-defined satellite. Generally they use this terminology for SATCOM type applications where you want flexibility to change your waveforms. It's the terminology. So these flexible SDRs are at the core of these software-defined satellites. So effectively, these flexible satellites, you can refresh them, reconfigure them on demand, right? You can update your waveforms, provide more capability. If you're using beamforming antennas, you could change, the pattern on the LAN so that you could, change your customer set, who are your customers. So again, and what's at the core of these, software-defined satellites is in fact these MPSoC, FPGA-based OBCs. If you get down there, right in the middle of there, that's at the core. So definitely a game changer. It's a game changer, and I would say it's being adopted today as we speak.
There's sort of knock-on challenges then for other aspects of engineering, I guess. You think if you're developing a system, software defined or otherwise, that has a much longer term upgrade path available to you than you're traditionally used to, you have to think about making other aspects of the satellite work for their whole mission lifetime. So I think how the engineers approach these systems, how they can deal with these systems, is important as well. So how do you think on that? How do you think that engineers may be able to? How well do you think they may be able to adapt to the use of FPGA-based system-on-chips OBCs if they are more used to the traditional, microprocessor-based OBCs?
Okay, so I think in general, if you look at if you look at these FPGA-based OBCs, you need two fundamental skill sets. One is software, and the other one is logic development. Right. So, VHDL or Verilog and so on. Now, honestly, so if you look at software, that's, that skill set, actually, in fact, both skill sets, both logic and software are very, that's a very typical type of skill set for any microprocessor, microcontroller-based system. Because, of course, you can have your processor, so that's the software side. But generally, in today's systems, you also have FPGAs, right? Because you want to leverage the kind of the level of integration, the horsepower the flexibility that can provide. So a lot of modern, if you break even a traditional traditional processor-based OBC, you pull out a peripheral board or two, there'll be an FPGA in there. So in general, the companies generally have these skill sets anyway. Companies like Xiphos and probably other companies like us, we also offer the capability to, if a customer is not comfortable with logic, we could develop logic, right? So the customer doesn't have to have that intrinsic capability. Or often customers, what they'll do is they'll subcontract that to a third party because they're doing some very specialized algorithm that they know a company has done in the past. So you don't necessarily need that intrinsic capability, but obviously it helps because it provides you more. It costs you less because you're not subcontracting and so on. So now, if you look at what does our processor come with? It comes with the Linux SDK, software development kit, just like if a processor is Linux based, they'll provide the same. So we provide all the drivers and the kernel and all the tools that you would require for a customer to develop the application software for their mission. So we provide that, but so would a standard OBC. We also provide something, for example, called the Vivado Skeleton Project. So that's a Xilinx tool where you would integrate your logic and so on and compile your logic. So we provide that so that if a customer wants to do custom logic, they just put their custom logic in along with the logic that we provide, and then they can compile an image based on that. Now, I mentioned that if you're designing an MP-SoC based solution, you'll need a custom daughter board, right? Now, as a traditional OBC, maybe you can find all the peripheral boards you need, and you can rack and stack your subsystem, but often there's probably some custom thing that you're going to have to design anyway, so you're going to need some hardware capability. So it would be the same thing here, right? To develop that custom daughter board would be the same as developing a custom peripheral board for a traditional OBC. But that being said, if a customer maybe they're too busy, they're juggling too many balls or they don't have that intrinsic capability, companies like Xiphos, we can work with them to, develop portions of the solution. We can develop the custom daughter board. We can develop any custom logic, all the way to a kind of a full turnkey. So, it's how we work is flexible, and it depends on the capabilities and the bandwidth of the customer, and really what they want to focus on. If they don't want to focus on the hardware, they want to focus on, their ground software so that they can make sure that they maximize the revenue. Then fine, we'll take care of the hardware.
Yeah, absolutely. Okay. And so aside from the skill sets involved that the satellite engineer would need or would need to be able to access, are there any sort of significant differences in the processes involved, the assembly, integration and testing, AIT processes that the engineers or the systems engineers might need to tweak if they were using FPGA-based systems on chips? Or
yeah, okay, that's a good question as well. Okay, so
or qualification and regulatory compliance, is another aspect of this, perhaps.
Okay, but I would say that, like, in general, the procedures are similar. You're testing a hardware platform. You got to test all your interfaces. You got to make sure here's your set of requirements. You got to make sure that your system meets your set of requirements. So, like, in general, in terms of overall philosophy, AIT, I would say, is the same. But I guess with the let's say if you take a traditional OBC where you're racking and stacking peripheral cards and you don't necessarily have to worry about logic, so that's you're basically testing at an interface level and so on, and just maybe testing your software, right? So with the OBC, with the FPGA-based stuff, if you're gonna do custom logic, well, then that adds a little bit to the mix, but it also adds to that capability. So let's say you took a traditional backplane based OBC, so racking and stacking with a backplane. So I don't know. So if you were integrating the system or assembling it and integrating it, you could test, for example, each board at a time. You test the functionality of each board. You might have some general test set which has a backplane, maybe a golden processor board that runs all your test suite, and then you'll test one board at a time, and then ultimately you'll put this all together, and then you'll test your software. right? And then you'll go through your validation steps, and then, like you said, qualification steps and so on. But that's, again, qualification, like environmental and stuff. That's par for the course, right? In our business, that's par for the course. So it would be the same. Once it's integrated in a box, it all kind of looks the same. It's just our solutions just tend to be smaller. That's all. Now, when you have an MP-SoC FPGA solution, so let's say, for example, you want to do some custom logic, or you want to interface specific type of interface in logic. So you got to start first with that. So you got to develop those soft IP cores, those core functionalities for the interfaces and so on. And the MP-SoC itself is just more highly integrated, right? So now you're developing your FPGA logic for these interfaces and stuff. You then test it with, for example, you're going to need drivers, right? Because you're working with Linux, so you're going to need Linux drivers so your application can access it with the right API and so on. So you're going to start that level of integration. And then you're going to integrate all of that, including your software or maybe some test software, into the FPGA. Integrate that with the custom daughter board, which is your application-specific stuff. And now you're going to start testing this much more highly integrated package, right? But the principle could really be the same. So you could segment the testing, maybe even amongst different teams, to the individual functions or interfaces. So for example, I'll give an example. Let's say you had SpaceWire, which is a very common high-speed interface on satellites these days. So let's say you had SpaceWire. There's an IP core in there. There's some drivers that run on the MP-SoC. And then you may or may not have buffers on your daughter board. So then you'll plug that SpaceWire interface into some type of SpaceWire test set, and you'll test your SpaceWire functionality. Now, that's one group working with that board, and then you can have another instantiation of that board to test another interface, maybe camera link, or you want to test your campus interface and so on. So you could segment it. So effectively, it's like testing the individual peripheral boards of a traditional OBC. So a little more highly integrated in terms of getting access to stuff and so on. You might have to share things a little more. You might need a few sets to spread across your test team, but in principle, it's the same. And then in the end, everything goes together. Everything goes in its chassis. You make sure it meets its requirements. Like I said, par for the course for space stuff. So not a huge difference. I think it really depends on how much custom development you're going to do, and often some of this custom development is the IP of a company. It's a differentiator between one, Earth observation company and another. It's their secret sauce, right? And so typical OBC stuff, maybe a little. You can get much better secret sauce with an FPGA-based solution.
More herbs and spices in the secret sauce. Okay.
Exactly.
Great. Well, I think we sort of covered all the technical aspects I was going to ask you about today, and you've also touched on a number of the possible applications and today and for the future. So I wanted to just finally to wrap up whether there was any application areas or type mission profiles that you're most excited about with that based on FPGA, system on chips, or that such systems enable.
Okay. Like Andy, what's going to get me? What's keeping me excited about this? First of all, the new space industry is exciting just to begin with, right? I've been in the traditional space industry in the past. I spent many years doing that, and this is literally a breath of fresh air. The level of innovation, the level of risk taking that people are willing to take, the availability of small satellite launchers, small sat launchers, to kind of make it, democratize space. Now it's a great industry to be in, and I encourage anyone talking to their children to get them into the business. So really, as we were saying, with these FPGA-based, multiprocessor-based systems on a chip OBCs, they can be used pretty much for any mission profile because, again, they're extremely flexible, they're extremely scalable. So, you can start with first of all, the processes in general are low power, right? They use like I said, 60 nanometer technology. So in general, the amount of energy per MIP is very low in general. So it's scalable. So let's say, for example, you have a small 1U CubeSat, it's very limited space for solar panels, right? Not a lot of power generation on board. So, but it just needs a processor and it needs a few low-speed I/O. Okay, you could do that, no problem. Okay, but then I have another application which needs 10 spacewire interfaces, and it's interfacing maybe a whole bunch of other gigabit per second stuff, and it's got maybe Ethernet, and it's churning a lot of data. Well, okay, so then that capability is also possible within the same platform. Or maybe you might go from a Q7 to a Q8, for example, in our particular case, if you need that processing. But it's extremely scalable, right? So from a low power, super low power, all the way up to, maybe a higher power, much higher performance with very high speed interfaces and so on. So in general, because of that flexibility, I talked about, I love the new space market. It's because it's really been a boon to us. We've been doing this for 20 years, right? So originally we were much more niche, work with space agencies and so on, rovers, and, very early days of rovers and stuff was very niche, but it's really not kind of niche anymore, right? So today, CubeSats, even nanosats, micro, small sats, all those, they're being used today for applications that were previously only kind of reserved or associated with much larger satellite platforms, right? Because you didn't have the power, you didn't have the scale or the miniaturization required. But today the miniaturization is there, right? Even down to sensors, right? The sensors are being miniaturized, much higher resolution cameras, right? That in in tiny packages. So it allows even these very small CubeSats to do things that were previously not even really imaginable. So you got, like I said, miniaturization of sensors, like high-resolution cameras, multispectral imagers, hyperspectral imagers. You need very high-speed interfaces like LVDS, SpaceWire, camera link. The successor of Camberlink called Coax Express, which works at gigabits per second. You need these types of capabilities to be able to pull off the massive amount of data out of these sensors, right? So, and that's what these MP-SoC FPGAs are really ideally suited at, providing these very high-speed interfaces. But then the next question is, okay, so now I've got this really high-resolution, 4K image sensor on my little 3U satellite, and I just pulled in a whack of data. I pulled in gigabits per second of data in my little, 7 millisecond image of the Earth, right? So the question is, okay, what do I do with this data? So what's the distance? So that's where you have a disadvantage of a CubeSat. So the CubeSat, compared to like 150 kilo or 450 kilo type satellite, it's limited in its downlink, right? Because you don't have a 3-meter antenna dish hanging outside of your satellite facing the Earth, right? You've got, a small little, maybe if you're lucky, an X-band downlink and a small little antenna. So you're limited in terms of downlink, right? So what becomes important there is onboard processing. You can't afford to downlink all the data. Number one, it might take multiple passes over multiple ground stations. It might take, and if you don't have multiple ground stations, it could take a long time to download that data. So you have to be able to process those images on board and just take down the important artifacts. And then, of course, there's probably going to be some post-processing on the ground too. But you got to try to minimize that to try to make it as revenue generating as possible, right? Like the more often you can take your images and get those things down to the ground, the more revenue you're generating. If you've got to wait, a bunch of orbits before you can download a single image, well, your business case, kind of suffers. So it's really, really that revisit time is important. So really, I would say that the breadth of these applications is really growing, and in large part because of the capabilities of these MP-SoC FPGA-based OBCs, these processing systems. So it's created really an exponential increase in demand for these solutions. So in our case too, we've grown our team substantially. We've grown our capabilities. We've grown our product line to be able to meet these demands and the demands that are coming up in the future. So really, that's been exciting, and and the varied numbers of applications that we're actually involved in is also very exciting. So what excites me even more now is these FPGA MPSoCs, they're increasing in size, they're increasing in complexity and capability, but yet because the silicon processors continue to shrink, you don't have big power penalties, which is super important, right? For a satellite, like on the ground, okay, you're good, but in a satellite, you're very constrained. So for example, if I take a look at if I give, for example, the UltraScale Plus, you have a version that not only has all the stuff I talked about before, but it has an embedded H.265 video encoder. So you're able to do that video encoder real time on board the satellite, which is hugely important. Another one, which is super interesting, which we're actually looking at, is there's an UltraScale that has an embedded RF system on a chip, an RF SoC. So it's an MPSoC with an RF SoC. So this thing has 8 broadband RF transceivers built into the same silicon. So the capability, it's an 8-fold, like I talked about SDRs before, so typically you might have 1 or 2 channels, or typically even 1 channel. Here you're talking about 8 channels coming out of a single board, right? So these are the applications that they can bring, whether it be for beamforming or whether it be for maybe even radar applications. It's very exciting because we're enabling capabilities based on effectively what's available from these processors. So on top of that, you've got growing tools. So now, for example, Xilinx has tools to be able to compile AI code and to run it efficiently on these MPSoC FPGAs. So now, on top of I talked about onboard processing, AI is becoming very important in that domain, right? So now we have tools now that can help a customer take his AI algorithms and get them running on our processors. Is also super important. And last, but certainly not least, the thing that is super exciting, that excites me the most, is you and the rest of humanity, I would hope, is a return to the moon, right? With a goal of, eventually a permanent human presence there, and then ultimately to get to Mars, also with a permanent human presence. So that's really exciting. There's, a lot of focus, a lot of effort, multiple countries, also intrigued and interested in the same thing. So like for Xiphos ourselves, we're already going to the moon. We're going to the moon on currently three, possibly soon more missions. So we're manifested in there. So it's super exciting for us, the thought of being able to do that. So, like in general, we just look forward to, using our technology to kind of advance the understanding of these planets, the moon and whatever, and help, sustain our presence there, so that's super exciting.
Oh, fantastic. Well, yeah, like you say, I think everybody in the industry keeps at least one eye on the deep space applications of what they're doing. So at least one eye.
Oh yeah, absolutely. Yeah. You can't avoid it, right? Because every day someone else is landing on Mars, right?
That's right. So, well, that's brilliant. I think that's a really good place to wrap up. And I just want to thank you, Edwin. That's been a bit of a masterclass in FPGA-based systems on a chip. I think the engineers and the people in our community will have really learned a lot about the technology and its uses today. So we would like to say thank you very much for that.
Oh, it was an absolute pleasure, and I hope I didn't put a bit too much information in there, but I think it's important that people understand what is in the art of the possible with these things, because they just provide a huge amount of capability, and we have a lot of innovators out there, and I think with what's available today, those innovations are not limited really or constrained just by the fact that we have to do this in space on a very small satellite. We can do that now.
Excellent. Well, yeah, thank you for spending time with us today on the Space Industry Podcast. And to all the listeners out there, I just wanted to remind you that you can find out more information about Xiphos and about all of the products that have been mentioned here today on the satsearch platform, satsearch.com. You can also request more information about the systems, documentation, introductions to the company, requests for quote, everything you might need for your procurement or trade studies on the system. Thank you for listening to this episode of The Space Industry by SatSearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.